So today we're going to be talking about Mask ROM reverse engineering. For those of you who saw my lecture last year I explained the chemistry required in order to take apart a microchip, photograph the bare die of that microchip, and then from the die you can begin figuring out how that chip works and reverse engineering its behavior. One of the pictures that I had in that lecture is the background here. This is the Mask ROM for the MYK82. It is a cryptography chip made by Microtronics for the Forteza card. And it's of historic interest because this was the center of the Clipper chip controversy. The Clinton administration decided that they were going to backdoor cryptography for basically the entire country. We could all do secure telephone calls, like with a landline and a modem that would digitally encrypt everything. We could all do that as long as we had a backdoor so that law enforcement could still listen to our phone calls. The idea is that if law enforcement had some wiretaps on you, they could get a warrant, present the warrant to maybe the NSA or a different group, and then get back a key unique to your cryptography chip. And that key would allow them to decrypt your session key, which was revealed during the transaction, and then they could decrypt the entire phone call and hear everything that you said. At the time, this was pretty controversial and people were fighting back and forth about it. But what I wanted to do is I wanted to read the code that was inside of this chip. And last year, I got this photograph. And in this photograph, I have all 130,000 bits of the firmware. But at the time, I did not have software to reverse engineer those bits and to extract them. What I really wanted was not a picture. I wanted a text file with all of the bits in physical order as ASCII art. And I wanted a script that would convert that to a .bin file that I could load in IDA Pro or Ghidra or Binary Ninja for reverse engineering. So in this lecture, I'm going to tell you how I wrote that tool. It is available for free. It's open source. It runs on Linux, Mac, and Windows. You can get it at maskromtool.com. There are also tutorials to teach you how to do this yourself. I've published a photograph of the CPU from a Nintendo Game Boy. And with that photograph, you can follow step by step. And at the end of the tutorial, you will have the .bin file that MAME uses when it emulates that same Game Boy. To quickly recap, there are different types of memory inside of a chip. And there are also different types of read-only memory inside of the chip. In this lecture, we're not going to be talking about flash ROM or EEPROM or anything that can be programmed in the field. We are only going to be talking about Mask ROM, which is programmed by making the right shape in a mask at the semiconductor factory that stamps out all of these chips. Inside of the mask, you will have a little shape for every one, and you will have the absence of that shape for a 0. And what we are doing is we are trying to get a photograph that shows us that same shape, or something related to that shape, so that we can mark all of the bits out of the picture and work our way backward to a digital file. These ROMs are programmed at the factory, and like any other memory, they can contain both code or data as the designer chooses. They are not always visible from the surface. A lot of the photographs I'm going to show you today required chemical processing even after decapsulating the chip in order to remove the upper layers of the chip to reveal the bits. Or even further, some of these encode their bits as the difference between P and N silicon, which are the same color. So you need to chemically stain a difference into the colors in order to extract them. These mask ROMs are used in very, very high volumes. Changing the mask costs on the order of $100,000. So there's no point in using a Mask ROM if you are not making a bajillion of something. Examples of it include video game cartridges. Nintendo, Atari, Super Nintendo, they all use Mask ROMs. Bootloaders are also very common for that because all of the microcontrollers in the family will share the same bootloader, and you don't need to make that unique to the customer. They're also used for copy protection because very often these Mask ROMs are contained inside of the microcontroller that runs the product. When you buy an inkjet printer for $30 and then you have to pay $300 for ink, inside of the ink cartridge there will be a little microcontroller with a little Mask ROM that is responsible for proving that that cartridge is real. If you wanted to bypass these restrictions, if you wanted to read this code, if you want to archive these games, if there's no electrical connection, it's sometimes very handy to fall back on the photographic method. Here is a Mask ROM from the MYK78 Clipper chip. This was the very first chip that the public could buy with the key escrow cryptography so that Bill Clinton could spy on us. I'm going to zoom in a bit by taking one half of this image. In each row, you see that there's a little shape and that there are little dark spots. Each dark spot is a 1, and if there is no dark spot, that's a 0. Now, of course, I mean this in the physical sense. I might have that backward for any particular sample. After you get these bits out, it's a separate problem to descramble them and to move them from the physical order of bits to the logical order of the bytes. The tool that I wrote simply loads up the photograph. I give it a .bmp file or a .tif file. I then mark in that tool where all of the rows are and all of the columns. And wherever a row intersects with a column, that's where a bit is. The tool then uses the color at that point to identify what the bit is and to mark it all up. So all of these little blue and red squares are the bits that were found inside of this Mask ROM inside of this chip. The contents here, at the time that the chip was manufactured and sold to the general public, the memory in here, this contains the F-table structure for a cryptographic algorithm called skipjack. Skipjack was still classified in 1993 when this chip was available. So you could have gotten classified encryption technology from the US government just by purchasing one of these chips, getting this image, and extracting the bits out of it. They've since declassified it, which is particularly handy because I can confirm what this table has by comparing the PDF of the declassified algorithm to the photographs and the bit extraction that I've made in my lab. Now, I'm not the first one to build technology like this. There are basically two tools that you need in order to read a Mask ROM from the photograph. The first thing that you need is a bit extractor. The bit extractor, ROM par by Adam Laurie and bitracked by Chris Gerlinski are prior art for this. And the Mask ROM tool that I'm talking about today is my replacement for these tools. The bit extractor's only job is to begin with a photograph and to end with ASCII art of all the bits in their physical order. It would also be nice if it did things like error correction or design rule checks so that you know when you've made a mistake. But it's a second tool's job to convert that ASCII art over to the logical bytes. Zorom is probably the best that's available right now. It's by John McMaster. It's a command line Python tool. You give it the text file and you tell it what bytes you think are in there. And then it will give you all of the permutations that have those bytes. And then you spot check them. Like maybe you look at the disassembly and see whether or not the disassembly makes sense. Or maybe you draw the artwork. Like if you're extracting artwork from a video game, when you start seeing sprites or tile sets that are accurate, then you know that you've correctly interpreted the machine, correctly interpreted the bytes. I am working on my own tool for converting the physical bits to the logical bytes. That is not yet ready for release, but I hope to have it in the next 6 months. And I hope to have it better than XOR-ROM, but I'm not yet to that point. We're going to quickly review the chemistry that's involved. I'm not going to repeat my lecture from last year, but just to get us on the same page. There are basically 3 procedures that you need for extracting these bits. The first one, which you always have to perform, is you need to remove the plastic covering from the microchip. You need to get to the glass. I do this with 65% nitric acid and a hot plate in a fume hood, and I pump the air out. The second procedure that you have to do is delayering the chip. I use dilute hydrofluoric acid for this in the form of rust stain remover. What this does is it burns off the top of the chip and leaves only the lower levels. And that's how I get the top metal layers out of the way so that I can look at the bits which are often encoded on lower layers. And then finally, a third type of mask ROM will not be visible at any vertical height within the chip, because the bits are encoded as the difference between P silicon and N silicon, which are exactly the same color. For that, I use a mixture of acids called a dash etch, which turns silicon brown, but it turns P silicon brown a little faster than it does N silicon, and that creates a difference that I can then photograph under a microscope. This is the nitric acid that I use. I had this delivered to the mailroom back when I was a grad student, and the computer science mailroom was not happy having the skull and crossbone package sitting on a shelf while I was out of town and unable to pick it up. For larger chips, particularly old ones, or ones that you want to decapsulate without breaking the bonding wires or damaging the chip, stronger nitric acid is preferable. This acid, the red fuming nitric acid, has less than 2% water in it. And water will dissolve the acid salts that are left behind on the wires. As the metal interacts with the nitric acid, it kind of rusts a little. If there is water, the water will brush the rust off and allow the acid to go further and rust more of it. So if you have almost no water, like this acid does, you can burn through the plastic without damaging the metal, because the metal will be protected by a microscopically thin layer of rust. So we take the chip, we drop it in the acid. The acid turns green from the metal dissolving. We keep heating it up. Eventually we get the dye out. That little guy there at the end of my tweezers, that's what we're looking at. We then put it under a microscope. The microscope can show us the dye, but usually they're too big to fit within one frame. So what I'll do is I will take 3 frames and I'll line them up in the right way. So 1, 2, 3, and then I can combine them into a panorama that gives me the whole chip. When I'm doing ROMs, I do the same procedure, but under higher magnification and only in the area of the chip that contains the ROM. So first I'll make like a big picture of the whole chip, then I figure out which part I care about, and then I photograph that in obscene detail. At the end of this, I get like a full picture of the whole chip or the whole region. Delayering is necessary because in very few of these chips are the bits visible from the surface. An example in which they are would be the Nintendo Game Boy. The Nintendo Game Boy has a 256-byte program built into its CPU whose only job is to scroll the Nintendo logo from the cartridge across the screen and to verify that it is the Nintendo logo that they have trademarked. so that they can sue the living shit out of you if you include a Nintendo logo on an unauthorized game that has not been licensed by them. That is visible from the surface, but for the ones that are not, for the ones where you need to go lower, you use rust stain remover, this little stuff, and you have to use a plastic beaker because hydrofluoric acid will attack glass. It will dissolve it, it will etch it, it turns it foggy, and if you had it strong enough, you could burn all the way through a glass beaker. The effect of the delayering, this is the surface of the chip, and a lot of the details are kind of obscured by this filler pattern here that you can see under higher magnification. If we want to see beneath that, all we have to do is boil this in dilute hydrofluoric acid for a minute or two, and then the obscuring features that you see here kind of go away. And these are the same chip. This is about halfway etched, and this is a bit further down. And now you can see very separate organs within the chip. You can see that there are different memories, and CPU components are kind of grouped together. In the early chips, like from the 70s and the very early 80s, you can even reverse engineer the instruction set by reading the lookup table that is the microcode of the CPU. So now that we have the picture, I'm going to walk you through how these are annotated. Basically, we first need to draw row and column lines. We need to tell the software where every row is and where every column is. And if our pictures don't line up perfectly, we can do this in smaller segments. You can do a couple of banks in one row and then do another row separately. We also have to teach it what the difference in the color is between a 1 and a 0. And ideally, we would want this to be, we want a single color channel that has a bimodal distribution with one being a lot brighter than the other. And we only need this in one color channel. So we'll look for a difference in green, red, or blue, and then we sample on that color channel individually in order to get the best separation. And what you'll see is that very often there is no difference in one or two of these channels, and it's only the third at which we can tell the difference between 1 and 0. And you're going to see that the tool does a lot of the work for me. It marks the bits themselves at the intersections of the rows and the columns. So I only have to draw as many lines as the square root of the number of bits. I don't have to draw as many lines as there are bits. It also has design rule checks that will point out when I screw up. If I hit the button to mark a line twice instead of once, then I'll have 2 lines in the same position, and the software can recognize that and warn me that I messed up, and even show me where in my design that happened. And then it's very important to be able to import the difference between 2 project files. So when I'm working on a very big ROM, like the 130,000 bits in that cryptography chip, I'm going to make mistakes. I'm going to have dust on the chip. I'm going to have a photo out of focus. By importing the difference between 2 projects, I can compare the bits that they have, and every bit that I get correct will be identical in 2 or 3 or 4 recordings. But any bit that I screw up, I should uniquely screw up to one of the outputs. And by comparing them, I can figure out which way and correct it. This is our first target for today. This is a music chip. Back before we had computers in doorbells, we used little digital things that would have a little song to them. So when you power up this chip, it plays Fürelise by Beethoven on loop. That's all that this chip does. It has 3 pins. You give it power and ground on 2 of them, and the 3rd pin will output Fürelise. You run that to a piezo buzzer or to a speaker, and you have yourself a doorbell or an electronic greeting card. And let's say that we want to steal this music, but we want every note exactly as it happens in that doorbell. Well, first we look at the bits, and I think as this projector is set up, it's easiest for you to see on the left. You see how it's kind of like a checkerboard pattern, but some of them are a little darker than the others? Those dark ones are the ones, and every space where it might be darkened but is not, that's a 0. I draw a line through every row, and then I do the same through every column, so that the computer now knows a point within all of these bits. You'll see that my column line here is not directly in the middle of the bit. Instead, it's on the side. And I did that because the side of the bit has these little like dark brown thingies. And that's the spot that I'm interpreting the color difference from, because it's more apparent there. My software then marks these little squares at each of these positions. Coming down from the top in this column, the correct values, which it is not currently displaying, would be 0, 0, 1, 1. And as you look at it, you can see that the ones have these little dark bars on the side, and the zeros do not. I can then annotate the rest of the microchip. So now the software knows accurately where every single bit is. It just does not know the correct color yet. So the next feature of my tool is a bit histogram. So this graph here shows me in red, green, and blue how popular every single color position is. You'll see that some of them happen a lot. Like I have 37 bits that have a red value of about 191. And you can also see that my red has 2 peaks. There's one here, and there's one over here. And green as well has 2 peaks. Blue has less of a separation, so blue will probably not be the color that I sample on. If I drag out the green selector to 91, and I'm sort of selecting like right here in the middle of the green peaks, I don't get a correct interpretation. If you look at that white arrow, you'll see a position that is red. The software thinks that it's a 1, but it ought to be blue. The software ought to know that this is a 0. And you with your own eyes can see that it's a 0 because it does not have those thick bars on the side of it, like the 2 ones that border it do. And where there's one mistake, there's usually more than one. So here are some other bits that are mismarked. If we change from over here, the green marker, if you look at the targets of those arrows, if we move that into the red marker, so from green 91 to red 124, then suddenly all of those bits are accurately identified. So now we've got almost all of the bits from for release correctly extracted. When I say almost, though, the design rule checks are really important for recognizing edge cases. Maybe there's a little bit of noise just where we do the sampling. Maybe it's really close to the threshold, or there's the wrong number of bits on a row. In this case, the software tells me that I have 4 bits that are ambiguous. It puts a yellow box around it to tell me not to trust it. And when I click on it in the menu, it will jump to that position. Now, this is blue. The software thinks that it's a 0, but it's actually a 1, which I can tell by looking at it with my own eyes. So, as this happens for each of the bits, I can then correct them. I can tell the software that this needs to be blue, and then it disappears from my rule violation list. Whenever I export this file from now on, because of this green square around the blue square, the software knows that its own opinion of the value of that bit is irrelevant because I, as the human operator, have told it what that bit ought to be. When you have a project with a checksum or a self-test, you can sometimes even incorporate that into your export to know that you've got it perfectly matched. The next thing that we need, so we've got all of the bits marked, we need to be able to get it out of the software into something else. So I've got these different file formats that I can export as. If this happened to be a Mark IV chip or an ARM6 chip, I could just directly dump a .bin file with all of the contents ready to reverse engineer. Because those chips aren't very common, I usually start by exporting either ASCII art or a Python matrix. And then I can do like linear algebra commands to rotate the matrix around until the bits begin to make sense. If you are a student or if you just enjoy pain, you can also export it as CSV for use in Microsoft Excel or in MATLAB. And so at the end, we get these bits here, and these ones and zeros are all of the bits of for release. And if you interpret them correctly, you can play the music. There are a lot of little design decisions under the hood that helped out in this project. It scales rather well to hundreds of thousands of bits. And it does so because I used the Qt6 graphics framework. My code is written in C++, and so is the library behind it. And then it uses 2D acceleration for all of the graphics that come from your operating system. So if you're running like Mac or Windows or Linux, it will use your graphics card in order to pre-buffer things to make it render faster. I can also use the collision detection algorithms that come from this framework. So I'm not having to keep track of all of the bits myself. I can just ask, like, hey, are there any two classes of this type that happen to touch each other? If so, I throw a warning up. This makes the rendering very fast and allows me to navigate projects that would be too large for the pre-existing software that came before this program. It's also necessary to accurately align the bits. In order to do this, I sort all of the bits by their x coordinate. So I'm getting them like left to right, and I don't pay any attention to where they are vertically. As I begin moving right, I should see every bit in the first column before I finish seeing all of the bits of the second column. And the only tricky part is figuring out where the border between them is. I have like configuration entries that allow you to specify where the ending is if it gets it wrong. As soon as you have the first column, though, the entire rest of the interpretation can be taking all of the bits from left to right, figuring out which bucket it would fit in most reasonably among the bits of the previous column, and then adding it to a linked list there, so that at the end you get a linked list for every single row, and then you can transform it out from there however you like. Another important design consideration was that from the very beginning, I wrote this as both a GUI and as a command line tool. All of the important commands that you can do graphically, you can also script to have the computer run itself. So as I begin marking up mask ROMs, I give them a make file, and the make file will do the complete decoding from beginning to end. And this also doubles as an integration test for my software. So as I'm developing this, if I fat finger a command and introduce a C++ bug that causes it to crash, but it only crashes in some obscure way that I only used in one chip, I will still recognize that because when I type make in my project directory, it recompiles every mask ROM that I've ever annotated in this tool and make will error out if any of them fails to correctly decode. So we're going to go back a step, back to the Microtronic 78. This chip was supposed to be the solution to law enforcement access to all of our private communications. And it failed because of political backlash, but it also failed because it had a problem with it. And the problem was not that the backdoor could be used by any random third party. The problem was that if you understood how this machine worked and you understood the commands that it used, you could do safe cryptography even with the backdoored chip. There are a couple of papers by Matt Blaze that explain this in detail. These two little segments here in the bottom left, they contain the lookup tables for that cryptography, for the skipjack algorithm. And we can photograph them and we can read them out. And presumably, anyone else who wanted to could do the same thing. Like, it takes patience, but if you really have to, you can sit there with an old school microscope and without a fancy computer, without fancy digital photography, and you can just look at them in a row and read them out to a bored coworker as you sit there going 1 1 0 0 1 1 0 0 1 1. These are all of the bits. This is the entire table. So you need the patience to write down this many numbers, but you don't need fancy space-age technology to do it. If you decode that into bytes, you get this table, which is the F table, which, kind of like an S box or something in more modern algorithms. This was classified at the time that that chip came out. So there are secrets embedded in these chips that you can recover just through photography in order to understand how they behave better, or to reverse engineer what they do, even though it's a physical object rather than software. In later generations, they added software. So this is the Forteza crypto card. This came out in, I think, 1997. You would plug this into your fancy government phone, and you would make a phone call, and you would have all of the backdoors that the Clipper chip promised. You had a few more algorithms that you could use. But one of the big things that this chip introduced that the prior chip did not have was that it added an ARM CPU. So where this says LUTs, or lookup tables, that's the same F table that we saw in the prior chip. But there's a CPU in the upper right, and if you zoom in on it, it has an ARM6 logo, so you know exactly which architecture it is. The logo is backward for reasons I don't understand. I think it's like a photographic processing mistake. Now over here on the left, you have the main boot ROM for that ARM CPU. And we can see the bits on it. These little rectangles on the sides of the squares. Every rectangle is a 1. If there's no rectangle, that's a 0. And we can also see the entirety of the chip. And over here on the right side, you'll notice that the rightmost column is entirely dark, and the column just to the left of it is kind of split. It is dark on the right side, and it is light on the left side. Basically, each of these big columns is one bit of significance. Well, sorry, one half of a big column is a bit of significance. So as you read from the right side to the left, you see a column in which almost all of the bits are 1, another in which they're almost always 1, a third in which they're almost always 1, and a fourth in which they are almost always 0. 1, 1, 1, 0. In hexadecimal, that would be an E. Who here does ARM reverse engineering of 32-bit code? We're not talking thumb. Okay. Why is an E the most common letter that you see at the beginning of 32-bit ARM code in every 32-bit word?
Because that's the control bits, or essentially just 2 bits of jump or check.
Exactly. So every 32-bit ARM instruction begins with 4 bits that describe the condition code. On ARM, you can make a single instruction, any instruction, only execute if the flags are correct. 1110, the letter E, means that you will always execute that instruction. And because most instructions are always executed, most of them begin with an E. And you can see, almost from orbit, that therefore the most significant bit is the one on the right, and that you count leftward as you go down to 0. And sure enough, when you properly decode this ROM, that's how it's encoded. In order to get the contents of this out, I had to move to Bogota for a week. I checked into a hotel there, and I dumped these bits out, and I just sat and I tried every combination until eventually it came out. And it did come out. This is the very first row and the beginnings of the second row of the machine code of the bootloader of the Forteza card. Here's the Python code that does the encoding. It's really simple. You just go right to left, 32-bit words, start at the top row, work your way down to the bottom. You know that you're working your way down to the bottom because while we see bits as little dots up here, there are no bits in the bottom fifth of the image because that is unused, and as you decode it, all of these are zeros. So having the code dumped out, I can then run binwalk on it, and binwalk starts recognizing all of these ARM function prologues. I then throw it into Ghidra, and sure enough, these begin to line up, and these begin to decompile correctly. And that is how, with a chemistry lab and some patience and some photography, you can extract the secret bootloader from an NSA-designed cryptography chip from the 90s. Thank you. Do I have time for questions? Yes. All right. If we could get some questions, and if someone could grab me a water, I would be very appreciative. Yes.
So how long did this process take you for that chip, for the Forteza?
So in the case of the Forteza, it took me maybe 1 day for the chemistry. It took me maybe 3 days for the photography, because back then I did not have a microscope with a motorized stage, so I had to manually move it without moving it too far. Another day to get the images together into one big panorama that evenly lined up, because if the panorama images do not accurately match, your decoding gets scrambled. And then maybe 4 weeks to write the decoding software, the Mask ROM Tool. And then I had to move to Bogota, where my Spanish sucks and I didn't know anybody, and spend a week holed up in a hotel room decoding the order until it made sense. That final stage, the week of figuring out the order, is the next problem that I'm trying to solve by making a tool that will accurately figure out that order for RISC chips like the ARM. I also have some ideas about statistics in disassembly for recognizing when a near miss creates code that doesn't quite line up. Yes?
Is the image processing portion of that a good candidate for, say, image recognition AI, where you could, instead of getting every column and row, mark just a few, say this is what a 1 looks like, this is what a 0 looks like, and let it take it from there?
Right. So the question was whether AI might be able to help with this. So far, I don't believe so, because it's difficult to build a large training corpus. I have had luck with support for plugins to recognize different ways of interpreting the ROM bit. The idea is that some of these you can tell by a difference in color, but others you have to look for a line. And so I did a plugin that finds like a long strip through the bit and then looks to see if the color dramatically changes halfway. And in that, I'm able to recover more of the images that gave me trouble in the beginning. Yes, I got one more question, and you in the orange in the back, if you could quiet down a little bit. I'm hearing you louder than the people asking questions.
I'm just curious, why did you choose to go to Bogota?
I'm sorry, I couldn't hear. Could you?
Sure. Why did you choose to go to Bogota? Why was that something that you felt you needed to do?
Flights were cheap, and I've always felt illiterate for not speaking any Spanish. And after 1 week, I can now confidently use the present tense in the first and second person, and not much more. Me llamo Peggy Hill y yo soy Puerto Gringo. All right, well, thank you all for your time and attention. Sorry. We got one more.
So the trip to Bogota had nothing to do with classifications or crypto export. You're just trying to really not be distracted.
Right, I did not want to be distracted. Flights were cheap, and it's a beautiful town. It's like New York City if it weren't so dysfunctional and overcrowded. Yes. So Mask ROMs are still used today. As chips become more sophisticated, you have the options to use other forms of non-volatile memory. And it is a risk to the reliability of your product to use a Mask ROM if you're unable to patch it. For example, I reverse engineered a blood glucose sensor, the Freestyle Libra. You inject it onto your arm, and then you can use your phone and just sort of tap your arm and find out what your blood glucose levels are. For diabetics, this means that they can do more frequent sampling. They don't have to prick a finger each time. It's a great technology, and God bless them for inventing it. But as I was reverse engineering it, the majority of the software is made as a Mask ROM, and then it uses FRAM, which is a non-volatile form of random access memory. FRAM stores patches against the Mask ROM, so that if they make a mistake in the Mask ROM, they're able to patch it in more volatile memory, but they don't have to include enough of that volatile memory to contain the entire program. In that sensor, the thing is disposable. You inject it, it lasts 2 weeks, and you throw it away. They have 8 kilobytes of code to implement that program, but they only have 4 kilobytes of FRAM, and in order to make all of this fit, they have to split it across the 2 memories. Another technique that you can use in a very modern chip, like if you're at a company that designs chips, you can implement your ROM as a sea of gates instead of implementing it as a regular array like this. And this has a performance penalty and it has a density penalty, but it is a lot harder to reverse engineer because the engineer needs to figure out all of this gobbledygook that was made by a Verilog compiler during the place and route stage, rather than something that is regularly arrayed and designed by a human being. If you would like to see the design side of this stuff, the Open RAM project now includes a ROM for the Sky 130 manufacturing process, which you can take apart and read. And I think that's about it. So thank you all for your time and attention, and I'll be around afterward if there are questions.